Okay, so now we have a discount factor, so we can define V star for our previous example, right? It doesn't go to infinity. So let's try to compute this V star value. Specifically the same question as we've seen before. What is V star for state cold? Okay, and we'll assume a discount factor of 0.9. This guarantees, and this is a geometric series, so this will guarantee that we convert to a specific value. It won't go to infinity. Okay, so let's try to compute V star cold. So we know that V star cold follows the action, the optimal action, the action that maximizes the immediate reward, plus the expected future reward, right? Which is just the probability of arriving at each one of the two states. The next state can be either warm or cold. So this is the probability of arriving at each one of these next state times the V star value of the next state, but we'll have to discount it once, right? So now we have a way to compute this V star value to state cold, and we're guaranteed that it will converge, even if we continue this process to infinity. So let's plug in the number, and we'll say that we'll take the maximum between two of the actions that we have, right? So we have to take the maximum of all actions. We can choose action fast or action slow. For action slow is a bit easier. So if we choose action slow, the immediate reward will be +1. Then we have a probability of 1 to arrive to V star cold. 1 times V star cold. But we'll discount the next step by 0.9. So we'll have to take the maximum between that and between choosing action fast. If we choose action fast, we'll see an immediate reward of +2. And then there is a 0.5 probability that we'll stay at state cool. And of course, I will take the V star value of that state multiplied by the discount factor. But also there is a 0.5 probability that we'll end up at state warm. Okay, and so we'll also need to take the state value for state warm with probability 0.5, and we'll multiply that again by the discount factor 0.9. Okay, so now we plugged in all of the numbers. We have several variables here, unknowns, right? V star cold and V star warm. And we'll simply compute this value. So what is the value here? Stack overflow, right? Why? Well, we're trying to compute V star cool with recursion and using V star cool without a stopping condition. So we'll get a stack overflow in this case. So how do we address this issue? We work in iterations, and this is exactly our initial solution for solving an MDP, which is value iteration. So we will update state values for our entire state space in iterations, and each time we'll compute another state value given the current assignments to the state values, and we'll continue to work in iterations and evolve over time, evolve the V values, the state values. So we can initialize the V values arbitrarily, okay? For instance, we can set them all to zeros, but it's not really important. So I will later show you a proof of convergence, and the convergence will apply to any way that you would like to, that you initialize your state values. But zeros is usually a go-to value. And then we work in iterations, right? We keep track of what's the change in the state value estimation, the largest change that we've seen throughout the state space, and then we'll continue to update these values until the change is lower than some small positive number. Okay, I'll show you later that the Bellman equation, the one that we're using here, is what's called a contraction mapping. So this guarantees it will guarantee that over time the difference in state values will converge when we update them, right? Meaning that this entire process will converge, however small of theta you'd like to set here. for your stopping condition. So what we do, for each state in the environment, we store the current value for that state, and now we update the state value for that specific state using the equation that we've seen previously, that is, we compute the expected sum of reward and the discounted value of the possible next state that we'll arrive at. We do that for all action, and we choose the action that maximizes this expected sum of rewards from this point onwards. And we set that as the state value. And again, during this process, we always keep track of the largest delta, the largest change in the state value that we perform during the current iteration. And once this change becomes small enough, we stop and we say that our process converged. Once the state value is converged, we can now output a deterministic policy. As follows, we simply compute the action. Now, instead of computing the maximum value, we compute the action. We return the action that results in the maximum expected value for each one of the states. The maximum expected G value, right? The expected sum of discounted reward from this point onwards. So after converging, after the state values have converged, we still have to have one more sweep over the entire state space in order to compute the optimal policy. Okay, so let's now try to compute the state values in our example, in our toy example. So now we should be able to be successful in doing so, right? Hopefully we took care of everything at this point. So again, we will compute the state values in iteration. So this is V0, V1, V2, and so on. And we're going to use what's called the Bellman operator, the operator that we just discussed previously. Right? We're going to update the state value based on the action that maximizes, or according to the action that maximizes the state value, which is just the immediate rewards that we're going to see. In the more general case, the Bellman operator is also defined over a reward function that takes into account the state, action, and next state. In our case, the reward function is only a function. In our case, is here in this toy example. The reward function only depends on the current state and the action that we're going to take, so we don't need to compute the expected value of the immediate reward over all possible next states. Right? So we can have a more specific Bellman equation where we take the reward function out of the expected summation over next states. But still, we need to add into that, for a specific action that we're going to take, we need to add the expected state value of the next state that we're going to arrive at, right? So we're going to iterate over all possible next states, and we multiply the next state value by obviously the discount factor and the probability of arriving at that next state. Okay, so let's start our process. The first iteration, let's say that we start, again, as I said before, we can initialize the state values arbitrarily. Let's say that we set it as zeros. And now we're going to start computing the state value in the next iteration. So help me out here. Our lovely TA will help me. So let's do cold V1 for code. So let's see. So we have two actions to choose from, right? So we'll have to iterate over them. We can either go fast or slow. If we'll go slow, let's do slow up here, and then fast down here, and we'll just take the maximum of both of these. If we'll go slow, the immediate reward will be 1, right? Mm-hmm. Plus, what are the possible next states that we're going to see if we do slow?
Just cool.
Just cool, right, yes. With a probability of 1, mm-hmm. Right? Yes. So with a probability of 1 times the discount factor is, in our case, what did we say? It's 0.9?
Yes.
So it's 0.9. Multiplied by the state value, mm-hmm. the current state value, right? In the current
Yes.
iteration.
Which is 0.
For, okay, right. Looking at the previous iteration. For that state, which is
0.
0. Okay. So the V1, the state value at iteration 1 for state slow is, in this case, it's just 1, right? So
1, yes.
1. Well, not exactly. We need to do the same computation for action fast, right? And then we'll take the maximum between the two. So what will happen if we take action fast? Let's see. Immediate reward is, let me out,
2.
2, right? Plus, now we have two different states that we can arrive at, right? Each one has a probability of 0.5.
Yes.
So we can arrive with probability at 0.5 at state
With the discount factor of
0.9
times it could go, if we go to state cool, then the value is still 0. And
right.
if we go to state warm, the value is still 0.
Right,
so
plus 0.5
plus
0.9 times 0 again. Okay, so all of this will be zeroed out. So we only look at an immediate reward optimization. That's actually the case for in iteration 1. So I will discuss it later, but value iteration can be seen as gradually increasing the planning horizon, right? At V0, we assume, okay, what would happen if we can take no action at the moment? Well, we see no results, right? 0. V1 is how can we maximize our reward in a single time step? V2 is 2 time steps, and K would be for K time steps, right? And at some point, since we have a discount factor, this is guaranteed to converge. We'll see the official proof in a second. So in any case, the value for state, the state value for cool would indeed be 2 in this case. What will happen? Can you answer quickly without computation? What is the state value at V1, at iteration 1, for state warm? So in state warm, we'll never take action fast, right?
Yes.
We'll always take action slow.
Correct.
It seems like action fast is just the wrong thing to do there.
So it'd be +1 again.
Right, you can either do slow and you'll see an immediate reward of +1, and the future reward, well, they're still dependent on zeros. So right, it seems like V1 for state warm is simply 1. And overheated, well, there's nothing much to do there. Oh, sorry. See, yeah, nothing much to do there. Game is over. Okay. And of course, we can continue this process, and you're more than welcome to do it yourself and see that you get these values. In V2, you should get 3.35, and then 2.35 for state hot. And you can continue this process. The interesting thing is, as you continue, these values will converge. The difference in these values will reduce, and you can continue this process until they reduce as low as you'd like. Okay? This is known as a contraction mapping. The Bellman equation is known as a contraction mapping. Bellman equation.